Okay, just a few things about dot product that we've already been over. This was the definition I originally gave, I should vote for definition. That's another definition. This is equal to this. So among other things, cosine of theta is going to be this divided by all this. And two vectors are orthogonal if A dot B is zero, because A dot B is zero, that means cosine theta is zero, assuming that neither A nor B is zero. Okay. And cosine theta is zero, circular definition, it's out here. Okay. Angle is zero. Now, cross product. R cross J is K. You notice that I and J are perpendicular. And K is perpendicular to both of them. And the right hand rule applies. I've talked about the right hand rule, haven't I? Probably not enough. So I'll talk about it again. But, okay, if I is in this direction, J is in this direction and K is in this direction, right? If I turn my fingers from I toward J, I get K, right? So I cross J gives me K. Note also, the magnitudes of these vectors are all the same. I and J are unit vectors. K is a unit vector. Okay. Whenever two vectors are perpendicular, the magnitude of the cross product is going to turn out to be equal to the product of the magnitudes. If the vectors are parallel, then the dot product is zero. So I'll write over here. By contrast, I cross I. I said dot product, I didn't say dot product, cross product, I cross I is zero vector. It's not zero, it's the zero vector. Okay. Just sticking with I plus I cross K. Take your right hand and tell me what the direction of I cross K is. Well, I is that way. And K is this way, right? So some of you are doing negative I because you're putting your fingers in this direction. If I is in that direction, okay, then your fingers have to go in that direction. Some of you are pointing at me. Okay, so you're pointing in all kinds of directions. You got to point south. Okay, that's not really south. South's about there, but that's as close to south as a wall gets. Okay, so there's I, right? Now you want to cross I with, if you cross I with J, there it is, right? There's I, there's J. Like your x-axis and y-axis. Now you want to cross I with K, you better turn your hand like this. Okay. So I cross K, what's this? It's negative J, isn't it? Make sure you understand that. Okay. And over here, all right. Any of these vectors, any vector crossed with itself gives you the zero vector. Okay. Okay, well, that takes care of I cross K. What's J cross K? It'll be J cross K. That's I cross J. You got to put your fingers in the direction of J. Okay, then you got to be able to cross it. Yeah, you got to cross it toward K. You got to do this. So if you're like this, you're crossing it toward negative I. Okay. So it's I. That's all you need to calculate a cross product. Now, there's a determinant definition or determinant calculation scheme. It's not difficult either. Okay, I don't recommend going to the determinant when you can do it more easily either. Because this is, I'm taking this as the calculation definition. Now, the definition of a cross product is it's a vector perpendicular to the two vectors you're crossing. And the magnitude is equal to the product of the magnitudes, just like A dot B times the sine of theta. Okay. It's a vector, whereas this is just a number. Okay. So it's a vector, it's perpendicular to the two, and it's perpendicular by the right-hand rule. So if I take the vector from that corner of the room up to that corner, from the low northwest corner to the high southeast corner, okay? And cross it with the vector from the low northwest corner to the high northeast corner, okay? So that vector has a direction like this, and this vector has a direction like this, right? So if I do that cross with that, point your fingers in the direction of that thing. Yeah, make your fingers parallel to the vector from that corner to that corner, okay? Now, you gotta turn your hand so that when you close your fingers, it points. And you turn that vector toward that vector, okay? So how are you gonna do that? Okay, you're up there and you turn toward that vector. Yeah, it's kind of like this. And it points up and back that way a little bit. Make sense? Okay. So you're going to see a lot of examples and get used to doing that because in order to visualize like electromagnetic fields and stuff, you got to really understand that. Okay. So it's going to be really important for physics. And a lot of the stuff we do in monoidal calculus or calculus 3 is closely related to physics. Okay. Because the whole theory of calculus 3 was developed to explain electromagnetic fields. Okay, that was the original impetus. It's also really important for hydrodynamics and a lot of other stuff. Okay, whole lot of stuff. Okay. Okay, so let's calculate that. Let's say that that vector is, we'll do it in meters, and we're going to say it's I plus 7J plus 3K. Okay, so let's call this our A vector. And our V vector, I'm saying that right, it doesn't have an I. It has, well, it's 7J plus 3K. Got it? Okay. Then I can find the angle between these two vectors very easily. Let's take the dot product. Dot product is 49 and 9, which is 58. Magnitude of this one, oh man, I'm gonna have to square thing. 64 and 49 and 9, which is 64 and 58, which is 122. Okay. And this one is square root of 58, square root of 122. So the magnitude of A pretty close to 11. Magnitude of B maybe 7.7. Just for ballpark. Okay. So we could calculate the angle. So theta is the inverse cosine of the dot product, which is 58. Or which is 58 over the product of these, which is about 80 something. Okay. So I mean, it's 77 plus 7.7, 84.7. Since this is an estimate, it just takes about 85, 58 over 85. $58 over 85 is a little less than 0.7. So I'm going to say that if you actually do this, I'm going to say it's about 42 degrees. Makes sense at that angle, and that should be separated by 42 degrees. It's not completely ridiculous. If I did that right, I might actually be close. So you can check me out. But I'm not claiming a whole lot of accuracy. Okay, so just to get a better picture of these angles. This doesn't, so we could then multiply this product by the sine. And we'd find that the sine is a little bigger than the cosine, but not a whole lot. Okay. So if we multiply those by the sine, we're probably going to get something in the 60s. Let's say 68, why not? Okay. So we can figure that out. Because we can do the cross product, use these definitions, and the distributive law. And in the process, we'll also get the direction of this vector that we got when we crossed it. Okay. And we get a unit vector in that direction. That's going to be really important. Okay, so A cross B is okay. By the distributive law, means we got 8i times 8i cross 7j, which is 56 times I cross j. And then we have 8i crossed with 3k. Okay. I could write this out as 8 times 7 times I cross j, and 8 times 3 times I cross k, just to make sure you see what it is. But do you see what it is without me doing that? You okay with that? Right. Okay, then it's what? Plus 7j across 7j, which is 49. J cross j. And 7j cross 3k, which is 21. Again, just distributive law. Okay. And then 3k cross 7j is 41 times k cross j plus 9 times k cross k. All right. Now you could write it out easily. You can follow what I'm doing. I mean, it's just, there's nothing to it. If your algebra is up to the distributive law, and I kind of think it is. Okay, now, a couple of things. We got k cross k here. What's k cross k? Well, any vector cross with itself is 0. So that goes away. Get rid of that term and we get rid of this term. Okay, they're gone. So now we write 56 I cross J. Now you can keep a table handy, so you always know this, but it's I cross J, that's K. Use your right hand. Don't use this, don't use Chang, use your right hand. And that's K. And it's 24 I cross K. I cross K is negative J. And then it's 21 J cross K. I didn't leave myself room, but then it's plus, again, 21 K cross J. K cross J is negative I. Okay. Screen keeps freezing up, but I haven't ever noticed it. Zoom doesn't keep up, so that's good. So it's 27 times negative I. Or 21 times negative I. And that's just 56K minus 24J. Okay. So actually, we kind of maybe had it going back this way, and a little bit this way. It's actually just plain in this plane here. Okay, it's only K and J, there's no I. Now, you're visualizing from back there. And when I visualize, I thought, okay. But when you work it out, you find out that it doesn't. And it really comes down to the fact that from that corner of the room to that corner, and from that same corner of the room up to that corner is all in a plane that pretty much goes from that lower edge of the room to that upper edge there. And that plane just cuts through the whole classroom lab, okay, in a way that has no tilt in this direction or this direction. It's all flat this way. No, none of this, none of this. And perpendicular to that has none of this and none of this. Now that's a lot to visualize and just move gesturing, but you want to think about this. Now, one objection I have to WebAssign is they don't really ask you to construct all that much. They just ask you to use these pictures that you can now manipulate with your mouse and rotate and all that stuff. That's good, but that's not construction. So I'm going to be watching some construction, okay? Because you don't really understand it if all you do is manipulate these pictures. Probably the best WebAssign can do. I mean, on the whole, I think WebAssign has a fairly good selection of problems, but I don't like the way they do graphs. They give you too much. They don't ask you to do anything. They ask you to explain what you see, but they don't ask you to construct it, for the most part. And then they give you multiple choice. And you don't want to know what I have to say about multiple choice. Start using bad words like favorite, stupid, bad education. They can't say those things. So okay. So that's an easy scheme, right? And well, it's totally equivalent to this. Another way to do A cross B. I guess I better get myself in. Okay, there are my IJK vectors. There's my 873 components of the A vector and 073 components of the K vector. Yeah, well, how do you do determinant? Now let me pause for a second. Okay, I had to stop, make sure everybody was familiar enough with determinants. It's very straightforward. Now, the way I'm going to write it is It's I times the determinant of the 7373. And you might recognize in linear algebra that the determinant of this is 0. So you don't have an I component, which we already found and we already even kind of explained. Okay. And then you got J times the determinant. Well, it's actually going to be minus J times the determinant of the minor you get when you eliminate the first row and second column. And that's going to be 8 and 3. And it's plus K times the determinant of (8707). Okay. And those determinants are really easy. I mean, this one's 0. I mean, if you like, you do 7 times 3 minus 3 times 7, but that's going to give you 0. Okay. And here you do 8 times 3 minus 3 times 0, which is easy. It's just 8 times 3, so that's minus 24J. And this is E plus 56K. I don't have to explain that, but you see that agrees with this. So it's easy to calculate. Okay, now here, I estimated that this angle would be about 42 degrees. So I could estimate the sine of 42 degrees, and I would say it's maybe 0.76. Okay. Product of the magnitudes is about 85.76 times 85. In the low 60s. I estimated it might be 68. Using the numbers, I get something a little bigger, but, you know, these are rough estimates. So I'll stick with my 68. I think it might be a little less than that. Okay. So let's see, the magnitude. And this is actually the kind of official definition. And then from what I did over there, I'm going to say this is a more honest estimate, might be 63 or 64. I'm going to say approximately 68. Based on my estimates, but of course, you can accurately calculate the magnitudes of A and B. So I think you're going to be pretty close to 85 when you multiply the magnitudes. I think we multiply by sine and theta is going to come out a little lower than that. Is a little more clearly. Okay, well. I don't know if I could. Well, 56 squared plus 24 squared, right? Well, 50 squared, well, 50 plus 6 squared is 50 squared. Okay. Plus 600. That gives me 3,100 and 36. And everybody knows that 24 squared is 576. Okay. And we add those up, we get 36, about 3,700. Add to the low 60s. More like 61 than 68, so I overdid it. Okay. So, 2 lessons, don't trust my estimates. 42 degrees, probably a little bit low. But there it is. Okay. Then I could do the A dot B, find the cosine from that, find the sine from this, and add their squares, it ought to give you one. Give you kind of a full circle. So nothing difficult then. So try to make sure you kind of really understand that because it's sort of foundational. Okay, it's about half and half, so we got it, so we didn't. What does it mean for A to be perpendicular to B? That means theta is 90 degrees, right? Cosine theta is 0, so A dot B is 0. Now you might just cut to the chase and think those that got it did. They knew A perpendicular to B means A dot B is 0. As soon as you know that that means A dot B is 0. I did mess up in the connection direction for the arrows over that indicate use a vector. And use one of the number of things. Well, that means that this equals 0, and that gives you a really simple equation to solve for A. Okay, so A is 5 over 63. And you can check that now. 5 over 63, 7 dotted with 5, 9. That's at 5 over 63. Almost as bad as thinking that the magnitude is going to be 68. Okay. The 3 over 5. See, good thing I checked, right? If I hadn't checked, I might have walked off and left that. Okay, 63 fifths times 5 is 63. And negative 63 over 5, right? Check again. Negative 63 over 5 times 5 is negative 63. 7 times 9 is 63. And finally, it adds up to 0. So after you see me make those mistakes, you won't feel so bad if you didn't get this right away. Okay. Whatever. All right, so I pretended to make those mistakes. Okay. Make sense? That's pretty simple. Okay. Well, I'm going to make it easy. I'm going to find a unit vector orthogonal to these two. Now, two things. If you got a vector, how do you get a unit vector in the same direction? Don't say anything. Talk about it for a minute. Okay, so I posed the question. How do you get a vector perpendicular to given known vectors? Or actually, how do you get a unit vector perpendicular to two known vectors? Because that's what I'm asking you to do. And I broke that down. You can break that down into two questions. First question maybe is, how do you get a unit vector if you know a vector? Well, you divide the vector by its magnitude. And maybe that's the second question. Maybe the first question was, how do you get a vector perpendicular to two known vectors? And that's what the cross product does. So just a simple two-step reasoning process. Two things that are going to become very natural to you because you do a lot of it. Unit vector, parallel to a given vector, and vector perpendicular to non-vector. So go ahead. Just see what you get in just a couple of minutes. And notice that we've already calculated the cross product of those vectors. They're the same ones we used before. Well, okay, so I'm going to find a unit vector orthogonal to these first. Equals, we do the calculation, determine the calculation or distributive law. And the distributive law is actually often quicker than the determinant if you've got a lot of zeros. If a lot of your IMJ components are zero, the distributive law just gives it to you real quick. Determinant's quick in those cases too. Okay, so A cross B is equal to what we got 56. Well, let's do it in order. Negative 24J plus 56K. Okay. In the definition of the cross product, tells you that. Wanted to find the angle, we could use that. The product of magnitudes, the inverse sine. Or do the dot product and all that stuff. Okay, so anyhow, then unit vector. Call it U. Cross product divided by the magnitude of the cross product. I'll use my estimate 85 for the magnitude. It worked out fairly well before. Okay. Now let's see, 25 over 75 be 0.33, your third. Divided by 85, it's a little less than a third, a little less than 0.3. So I'm going to say 0.29. Okay. Now 8 into 56 is 7. 9 into 56 is about 6.2. So I'm going to say it's about 0.66K. Okay. Now we could check. Is the inverse sine of 0.29 equal to the inverse cosine? Well, whatever. But we could have plausibility. Not equal to 1. Well, answer I get is no, not too good. Of course, the magnitude wasn't 85, was it? 85 was what I got when I took the product of the magnitudes of A and B. So it's a good thing I checked. Okay, well, having pretended to make that mistake, let's correct it. Got a magnitude around 61. I got to do live division all over. 60 into 24 be 0.4. Okay. 61 is about 1.5% more than that. 1.5% of 0.4. Okay, 0.3. Okay. And now. Dismissing this by 5/61, 5/61 is about. About 0.92. Right, I give or take a 10%. Check plausibility. And of course, you do this in calculators and stuff. The calculator agrees with me, then you know it's working well. Okay, 0.39 squared is going to be a little less than 0.16. Pretty close to 0.16. This is going to be pretty close to 0.84. Those are honest estimates. But of course, the 0.16 and 0.84 aren't really that accurate. Probably give or take a 10. Okay. Those are honest estimates, they just happen to work. Now it's technically used 0.15 instead of 0.16. So but you can work it out accurately to the within the limits of accuracy of your calculator. You get these and add the squares, you're going to get that. Use Excel. Now who knows what Excel is going to do. It's not really a mathematics program, but it's handy. Okay. Okay, so we already know some of the real essential stuff. Okay, well, there's more stuff. There's some geometric stuff, and the geometric stuff is super neat. What the heck? I'm going to use these vectors now. Okay. Okay, look. We got this vector and we got that vector, right? That's two vectors. Okay. That's one vertex of a parallelogram. That's another. Where's another vertex? Well, we got to go that vector in addition to that. So it goes way out in the hall, almost over to the next hall, right? So parallelogram goes up there like this, and then it adds this vector. Okay, then it comes back parallel to that one, and then comes back to this original point parallel to the other one. Okay, and we can draw that pretty well. It's in 3 dimensions, and I'm not going to put it 3 dimensions. I'm going to draw it from the perspective of somebody viewing this from the normal direction, the direction perpendicular to that plane. I said these two things lie in, right? So we're just going to kind of flatten that plane out and draw the vectors. And the vectors have magnitudes that I estimated over here of 11 and 7.7. So the first vector is longer. So we got a vector here. Oh, we'll just write it here. Doesn't matter. Got magnitude 11. Okay. We've got another vector, maybe here. It's a little shorter. Its magnitude is about 7.7. Okay. This is our A vector. And this angle is maybe 42 degrees or 46 degrees or whatever. Whatever. You got some angle. It doesn't matter. So we're just going to call that angle theta. And that doesn't look like it's in the 40s, okay? And I think the angle's in the 40s. So it's not an accurate, totally accurate. These things are separated by a little bigger angle than that. Doesn't really matter. We just want to figure out the area. Okay, so let's see. We go parallel to this vector, and then we go parallel to this vector. We want the area of the parallelogram. Now, I don't know what you know about the area of a parallelogram. But I bet you don't know what I'm gonna tell you. I want the area of this parallelogram. I'm just gonna chop off this triangle right here. And I'm gonna put it over here. It fits, all the angles work, magnitudes. This has the same length as this, I'd have drawn it that way. It probably particularly well, okay? And now it's a rectangle. And the dimensions of the rectangle are what? Well, the dimensions of this rectangle are magnitude of A, because what I added on here is just what I chopped off here. So length of this vector is the same as the length of the vector from here to here. Now, what's this side? Okay. Tell me how long this is, write it out. Not in terms of vectors or anything, just in terms of magnitude of B. Or if the magnitude of B is 7.7, you can even write 7.7. Okay, so, one thing I didn't say, might have been helpful, is this is an altitude, meaning it's in a right angle. Okay, so this is a right triangle that I moved over here because I said I'm going to get a rectangle. Now, if I'm going to get a rectangle, that means this had better be a right angle. Of course, this is the same angle this is. Okay, so now we know this is a right triangle. So and the opposite side is a magnitude of B sine theta. Because this side has length magnitude of B. If you want to write 7.7, that's fine. You recognize that that is the magnitude of B. And of course, this is the way we ultimately want to write it. I didn't care. All I wanted to see was you understand that this is a sine of theta times this. Okay. Okay, so now the area of the rectangle sure this is all coherent. Okay, so here's our triangle. We want to find this. And it's simply magnitude of B sine theta. And all these relationships with right angles ought to be second magnitude. And right triangles. Okay, so it's magnitude of B sine theta. So that the rectangle you can't read the first part of that because they're messing off, but it's obvious what I'm saying. Rectangle area equals a parallelogram area. Because a rectangle just consists of the area of this plus the area of this, which is the area of this plus the area of this, which is the area of the parallelogram. It's a rectangle area equals parallelogram area equals then we got the magnitude of A. This side is the magnitude of B sine theta, right? This magnitude across the product. Look out of my hand. Oh, don't make me feel that far. No. Okay. I'm happy to be able to leave. I get stiff when I don't move around. I'm still kind of stiff, even if I do move around, but not that stiff. Okay, A cross B, right? Magnitude of A cross B. So that's the area. Parallelogram. Okay, well. This leads us to one of my favorite things in the universe, which is the triple scalar product. Okay. I want to make this thing into a parallel type bed. Okay. Just means three-dimensional figure. Got a lot of parallel sides. Maximum number of parallel sides. Okay, three-dimensional figure formed of parallelograms. Okay. And specifically 6 parallelograms. Yeah, in whatever way you're going to define it. The idea is this is going to be the base. And our altitude is going to be some other vector. Maybe. Where's the likely vector? Oh, heck, let the altitude go from that lower corner of the room to that upper corner. So the altitude's like this. Okay. Actually, is that altitude in the plane? Couldn't be, it cuts right through the plane. Okay. Okay. I'll last 16 more minutes. I think my brain is keep working that long. Okay. Triple scalar product. So here we've got A and B. And here, I'm going to draw another vector that isn't quite the vector that I was talking about. But here's A. Here's B. And here's C. I can complete this parallelogram. We're going to use that parallelogram as my base. And then I'm going to come out. So I could draw vector. And then I'm going to come out in this direction like so. From each of these. So now I've got a three-dimensional figure. Okay. What's the volume? Well, pretty simple. Volume is the area of the base times the altitude. Just like over here, the area was the length of the base times the length of the altitude, right? And of course, this is an altitude, and altitude is defined as something that comes off for a two-dimensional figure, something that runs from one side of the parallelogram to the other, perpendicular to one of the sides. And that side becomes the base, and the perpendicular then becomes the altitude. Okay, perpendicular distance is the altitude. Okay, well, it's the same thing here. But it's the area of the base times the altitude. We already know the area of the base. It's A cross B. It's the magnitude of A cross B. Okay. So we've got A cross B. Let's say A cross B is here. And the length of A cross B is the area of the base. The altitude has to be the component of C perpendicular to A cross, parallel to A cross B. Okay. So we project this C vector, I'll use a different color here. We project the C vector onto this. Okay. And now this vector is an altitude. Here's our C vector. There's our altitude. Okay. Our altitude we call this angle theta. Now I'll use theta over here. So I'll go ahead and use phi. Length of the altitude is magnitude of C. Well, in terms of the magnitude of C, which is the length of this side, and the angle phi, how long is that altitude? Write it out. Length of the altitude is what? You've got a triangle here, and of course you always project at a right angle. Okay. Now I screwed up and didn't turn the video on. I don't remember where. I'm probably going to go back a little further than I need to. But I think we did see the rearrangement of the parallelogram with sides B and A. And quite here, there's the arrow to this vector. Here's this vector. Magnitude of A is 11. And I should use magnitude sign. Okay. And we chop off this triangle, slap it down over here. And we now have a rectangle whose area is equal to that of the original parallelogram. We look at this right triangle here, because it's a right triangle. The reason it's a right triangle is we're making a rectangle out of it. So this has to be right angle, meaning that this has to be a right angle. We chop it off. So the right angle, and put it back over here. So that this is an altitude that's perpendicular to the base. It's the altitude of the parallelogram, and it's the altitude of the equivalent rectangle. Okay, so I think we've got all that. We convert the parallelogram with legs defined by the vector A and the vector B, convert it to a rectangle, and we observe. Okay, people do not always write this down. I asked, what's the length of this in terms of the symbols we got here? But this angle is theta, and this is a right angle, and this side has magnitude equal to the magnitude, it has length equal to the magnitude of B. Then this is magnitude of B sine theta. Here's your right triangle, here's your opposite side. Here's your hypotenuse. So right triangle, opposite side is magnitude of B sine theta. So now our rectangle area, which is equal to the area of the parallelogram, is going to be the length of the base, which is magnitude of A, times the length of the altitude, which is magnitude of B sine theta, which is A cross magnitude of A cross B by the definition of the magnitude of the cross product. Okay. Now, even neater than this is a triple scalar plot. Okay. So what we do is we have A here, we have the B vector here, and we have a C vector here. The C vector I ultimately chose was the C vector from the lower northeast corner to the upper southwest corner of the room. And turns out that vector is negative 7j. Our vector is and it isn't negative 7j plus 3k because it's also got an odd component. Okay, the vector from there to there The I component is going to be 8I. Okay. And that's kind of helpful. Okay. Numbers still don't turn out. Okay, well, let's see what we're doing. Okay, so we've got this vector, which is, got a vector goes that way and a vector that goes that way. Okay, they're not parallel. One goes from lower left to lower right to from that lower corner of the room to that lower upper corner of the room, a diagonal. Okay, and the other goes just diagonal along the wall that we have there. And those are our A and B vectors. Okay, so we get the area of the parallelogram just by doing A cross B taking its magnitude. That's going to be the area of this thing. Now we have the C vector, which goes at a pretty big angle like that way. Cuts through the parallelogram and so forth. Well, the C vector we're going to depict here. The C vector that I'm actually using is at a much bigger angle with the A cross B vector. Well, makes a much bigger angle than the one I do here, single fly. Okay, well, what I have in the picture then is the A cross B vector, which is perpendicular to the A and B. Right-hand rule tells you it's in that direction. There it is. And that's perpendicular to the parallelogram. Well, the altitude of the figure that we get, if we complete this six-sided figure with sides parallel to A and B and C, you see the figure here. This vector is parallel to C. This vector is, well, this vector is equal to the C vector, just in a different place. This vector also equal to the C vector, and this vector here also equal to the C vector. You see how that goes together to make this a three-dimensional figure. We're trying to find the volume of this stuff. Okay, now what's the volume of the three-dimensional figure? The volume is the area of the base times the altitude. Okay, well, we know the area of the base, we just have to find the altitude. And it's not altitude, it's just altitude. The A cross B vector is perpendicular to the base. The altitude has to be perpendicular to the base. How far is it from here up to here? Along a vector that's perpendicular to the base. And that's our altitude, and that's the projection of C onto the A cross B vector. So we just take this vector and we have dotted lines that go across here at a right angle to the A cross B vector, and there's our altitude. And what's the length of the altitude? Well, I did some stuff down here and I kind of got a little crowded and started it over again here. But the length of the altitude is the magnitude of C times the cosine of this angle phi. I mean, here's a right angle, right triangle. That's a right angle with the projection. So this projection line and this vector and this vector form a right triangle. Right angles here, phi is here. This side is adjacent to this angle. This side has length equal to the magnitude of C, so the length of the altitude is magnitude of C cosine theta. And I kind of got a little off track here. So the volume's area of the base times the altitude. Well, it's then the magnitude of A cross B times the magnitude of C times the cosine of phi. Magnitude of A cross B is the area of the base. Magnitude of C cosine phi is your altitude. You multiply all that out, and then we say, well, that's the absolute value of the dot product of C with the A cross B vector. They didn't have room to really make that clear. So we came over here and just isolated our A cross B vector and our C vector. The length of the A cross B vector, magnitude, is the area of the base. The projection of the C vector, the scalar projection of C vector onto here is magnitude of C cosine phi. It's our altitude. Here's our altitude. Here's the area of the base. We multiply our altitude by the area of the base, the length of this vector by the length of this vector, and we get the volume of the parallelepiped. Well, let's observe that magnitude of C cosine phi Well, let's just do this. Okay. I'll just skip to the chase. C dot A cross B is what? Magnitude of C, that's the magnitude of A cross B, just by definition of dot product, times the cosine of the angle between, which is 5. So, magnitude of A cross B is your area of the base, and magnitude of C cosine phi is your altitude. So this triple scalar product gives you the area of the base times the altitude, which is the volume. And then we calculated it for the C vector and the A cross B vector that we've been using for a while. And the A cross B vector, here we have it. And then C dot A cross B is this. And, you know, no, it's all good. Okay, there's your C dot A cross B, we'll get 336. Okay, it's a very simple calculation. Once you have a cross product, once you have C, just do the dot product, and that's the volume. Now, that's a picture that's really worth understanding. Okay, your book has a picture that's almost as good as mine. Okay, well, nothing to do with that. Okay, so the book has good pictures. Understand this. I know when I understood this, I thought it was really neat. Okay, that's really kind of one of the big things you learn to understand in a calculus 3 course. One of the easier big things to understand if we understand a little bit of geometry, what volumes mean and what areas mean. So reconcile this as best you can. To the best of your ability, it'll be worth it. Did have a question somewhere. Why did I use single absolute value signs here when I had double absolute value magnitude norm signs here? It's because C dot A cross B is just a number, whereas C is a vector, A cross B is a vector. Okay, it's a vector, we do magnitude. If we do numbers, we do absolute values. Sometimes I screw that up, and I did that over here. So we correct that I can submit over there. But there we have it. Triple product and cross product as the area of a parallelogram. Important geometric ideas. And not sure that this board is totally visible. What have I set off? Not much. Okay.